Hello and welcome to Principles of Mathematics lesson number 8. In this section, we're going to look at subtraction of whole numbers, and basically we're going to be looking at the meaning of subtraction by studying various models, the inverse relationship between addition and subtraction algorithms including the standard algorithm and how to use them, subtraction with number bases other than 10, and mental subtraction, computational skills, and estimation techniques. All right, one of the most basic ways that we teach elementary students about subtraction is using the takeaway model. Suppose we want to teach them how to handle 8 minus 3. So we start with a bag with 8 blocks in it, right? 8 cubes, and we go ahead and remove or take away 3 of those blocks. That way the student can see that we're now left with 5 blocks. Very effective and very elementary. For the next model, which is called the number line model, we basically start with the first number and it's a positive 5, so we know we put the end of the arrow at 0 and the tip goes at 5. So instead of adding another arrow of length 3 at the tip and going in the same positive direction, this time we put the arrow and point it toward the opposite direction. So this way we take away and where we end up is going to be the result of our subtraction. Again, another visual method which is popular with young students. All right, another model is the missing addend model. So what we do is we take this subtraction problem, 8 minus 3 is what number, and in turn we turn into this addition problem with a missing addend. So we say 3 plus what number gives us 8? Because that would be the number that would be obtained if we took 3 away from 8, right? So, and of course we know that the answer there would be 5. Therefore, the answer to our subtraction problem is also 5. Visually speaking, the missing addend model would look like this. Basically, when we want to handle 8 minus 3, we say 3 plus what would make 8, and of course that would be 5 of those cubes, right? We can even demonstrate that on the number line by starting with 8. So we have a positive directional arrow with length 8, and then we put an arrow of length 3 at 0 as well, and say, okay, how many more places would we have to move in order to get to this 8? And of course, again, the answer will be the same, 5 units. In fact, we have the formal definition of subtraction in the following manner. We say for any whole numbers a and b such that a is greater than or equal to b, a minus b is the unique whole number c such that b plus c equals a. So this is very consistent with the example that we just saw, right? So we say 8 minus 3 is equal to 5 if and only if 3 plus 5 equals 8, and 5 would be that unique number c that we're looking for. So anytime you look at an abstract definition like this using letters, to make it come to life for yourself, just do a real life example with more concrete numbers, and that will really help you absorb why the more abstract version may make sense. Here's another helpful model called the comparison model. Juan has 8 blocks and Susan has 3 blocks. How many more blocks does Juan have than Susan? So we just lay out the number of blocks that Juan has and the number of blocks that Susan has, and then just count how many more. We just do a 1-to-1 correspondence between the ones they do have in common, and then just count the number that Juan has that is outside of that correspondence, and we get our answer. Now, if you recall, when we had the operation of addition of whole numbers, that operation we found out is closed. In other words, not the operation itself, but the set of whole numbers is closed under that operation of addition, because anytime we have two whole numbers, the sum is also going to be a whole number. Now, it turns out the set of whole numbers is not closed under the operation of subtraction. Because remember, in order to make that statement and prove it, all you need is one example that shows you the fact. Like, suppose somebody makes the assertion that the set of whole numbers is closed under subtraction. To prove them wrong, all you need is one example. Well, here's a simple example. If you take the two whole numbers 3 and 5 and subtract them, the result is going to be -2, which is not a whole number. So this shows you that the set of whole numbers is not closed under the operation of subtraction. The process that we just saw is kind of a segue into introductory algebra using whole number addition and subtraction. Sentences such as 9 plus 5 equals, some shape that we use, like a star or something like that, or 12 minus diamond equals 4. They can be true or false depending on the value of the shapes, right? Whether we use a star or a diamond. For example, if the star is 10, then 9 plus 5 equals this star is false, because we know that 9 plus 5 should be 14. So if instead of 10 we had 14, 9 plus 5 equals star would have been a correct, true statement. If the diamond is 8, for example, in 12 minus diamond equals 4, then that statement would be true. If the values that is used makes the equation true, we say that it is a solution to the equation. So take the equation 12 minus diamond equals 4. The value of 8 for diamond makes the equation true. That's why we say 8 is a solution of that equation. All right, next we're going to take a look at a concrete model algorithm for subtraction. And for that, we'll go ahead and visit YouTube.
Hello, this is Samantha from SPO Resources. And in this video, I will show you how to use base 10 blocks to subtract 3-digit numbers with regrouping. First, let's look at the number we are subtracting. 343 minus 224. I will start by using my base 10 blocks and dragging them onto my place value mat to represent the top number, 343. Now that I have shown 343 on the place value mat, I can use my takeaway marks to show subtracting 224 from 343. I will start in the ones place. First, I need to subtract 4 ones from 3 ones, but I don't have enough ones to subtract, so I will need to trade 1 10 for 10 ones. I can do this by moving 1 10 into my 10 box and dragging down 10 ones. Now, in the standard algorithm, I no longer have 4 10s. I have 3 10s. So I'll cross out the 4 and put a 3 on top. I also no longer have 3 1s because I added 10 more 1s. I have 13 1s, so I'll cross out the 3 and write 13 in the box. Now that I have 13 1s, I can take 4 1s away. After taking away 4 1s, I am left with 9 1s. I will type 9 1s in the box. Now I need to take away 2 10s from 3 10s. I am left with 1 10. And finally, I need to take away 2 hundreds from 3 hundreds. I am left with 100. Moving over to my standard algorithm, 13 minus 4 is 9, 3 minus 2 is 1, and 3 minus 2 is 1. I have the answer 119. When I look at my place value mat, I see 100, 110, and 9 1s. Now it's your turn.
All right, so that was a very nice video showing us a concrete model for the subtraction algorithm. Again, very much in line with the standard algorithm, but done in a nice visual way that younger students can understand and comprehend. All right, next we'll use a very useful technique called Equal-Addends Algorithm. And this relies on the fact that the difference of two numbers is not going to change as long as you add the same number to both of those numbers. So here we notice that we can quickly get from 163 to a multiple of 10 if we just add a 7, right? So that's what we'll do. We'll go ahead and add 7 to 163. That gives us 170. And of course, we're going to add the same number to 255 so that our subtraction problem's result does not change, right? So we end up with 262 minus 170. And now we'll apply the same trick again, this time going from 170 to a really nice number, 200. So that would require us to add 30 to both of those numbers. Now, in this figure, if you had actually, this would have been a little bit better if you had put the parentheses that you see here that they utilized in this step as well, okay, just to be really consistent. All right, so here we end up with 200 for the 170 plus 30, and that becomes 292, which we can quickly subtract and get 92. So it's a really helpful technique so that we end up only working with really nice numbers in accomplishing our task. And more than, any of these techniques themselves being super significant, just your mind's ability to be able to see the same problem in different ways adds great mathematical depth to your repertoire, and helps you understand concepts more readily and makes your mind ready for understanding new ways of seeing older concepts. And that's what's really important here. All right, here's a nice algorithm called counting up algorithm. In this case, we're trying to get from 31 to 100 to see basically how far we need to go to do that, right? So we start at 31 and we quickly get to a multiple of 10. And of course, the first multiple of 10 is 40. We know we need to add 9 to get to 40, right? So now it's a much simpler task of getting from 40 to 100 because we know we only need 60 for that. So that just adding the two distances that we traveled, it was what, 9 and 60, so we get 61. And of course, we can verify this using the standard algorithm, right? And just subtracting 100 minus 31. Of course, 1 can't be taken away from 0. We have to borrow here. There's not enough in the next digit, so we have to go to the next one and borrow. So we get 0 here, and we get 10 here. Now we still need to work on this, so we need to lend one of these 10 to this one, so this becomes 9 and this becomes 10. So 1 from 10 is 9, 3 from 9 is 6, of course, as we expected. All right, so this counting up is really nice method. You can actually do this kind of thing in your head. All right, here's a quick application. Noah owed $11 for his groceries. He basically handed the cashier a $50 bill. When handing Noah the change, the cashier said, okay, started with 11 and then said 12, 13, 14, 15. What is she doing? She's trying to count up to 50, right? And then once she was done with the handing the ones back, she then said 20 and then 30 and then 50. So that means, look, starting with 11, that's the starting point. So Noah is not getting any money there because that's how much he owed. So starting with the 12, we know there's 1, 2, 3, 4 ones, right? And then jumping from 15 to 20, that must have happened using a 5, right? And then from 20 to 30 using a 10, and then a 20 to get to 50. So basically, to see how much change he got back, all we have to do is add these, right? So 20, 30, 35, 39. All right. All right, here's a nice algorithm called trades first algorithm. In this algorithm, which is similar to the basic standard algorithm, what we do is we do any trading that's required and regrouping first before we do any subtraction. So let's say we want to handle this subtraction, 235 minus 147. All right, so we go ahead and write the numbers as usual. I like to leave space between digits so that I can work more easily with them. All right, so here with this, it usually kind of helps to work your way from right to left. So notice here we don't need any kind of borrowing because this is fine, 1 from 2. So moving on to the next digit, we know 4 can't be taken away from 3, right? So we know we're going to have to borrow, right? So we borrow 1 from the 100. That means we're going to add 10 tens to this place, right? So of course we have 3 tens already, so now we have 13 tens. Now we also know we can't take 7 away from 5, right? So therefore we're going to have to borrow some. So we're going to borrow 1 10. So this becomes 12 tens now, and we're going to add 10 over here. We have 10 ones, so we have 5 ones. So adding those 10 ones will make this 15. All right, see, this algorithm, we are now ready to go. And the nice thing is that we've taken care of any kind of trading that's needed already. So we can go ahead and subtract. Now, before we had to always go from left to right. The nice thing about this algorithm is it doesn't matter which way you go, because you're not going to run into any situations that are going to cause you any difficulty. So either go from right to left or left to right, whichever you like. I'll just stick to right to left. 7 from 15 is 8. 4 from 12 is 8. And 1 from 1 is 0. So which we don't need to write. So we just end up with 88. Try it on another problem for yourself. See how nicely it works out. All right, so now let's take a look at a subtraction in a different base. We already looked at addition in a different base. Let's take a look at subtraction now. It kind of works similarly. You have to be a little more careful, perhaps, as usual with subtraction. A little more care is needed than with addition, right? So let's, for a minute, assume we were just subtracting those in base 10. Let's remind ourselves what we would do. In other words, imagine I was just looking at these two numbers, but they were in base 10. I would just have 432. Notice I can say 432 now because I'm looking at a base 10 number, and then 43, right? So if we were to use the strategy which we just learned, which was the trades first strategy, it would end up like this. Now we know I can't take 3 ones away from 2 ones, right? So I would go to this column and I would borrow 1 10, right? So that would become 2 10s now. And this one here would now become, we already have 2 ones and we borrowed 10 ones. So this one would become 12, right? Now, looking to my left, I noticed that I cannot take 4 10s away from 2 10s. So I would have to go to the hundreds column and I would have to borrow 100. Here, this becomes 3. And remember, 100 is 10 10s, right? So I'm lending 10 10s over here. I have 2 10s already. So 10 10s would make this 12. So I'm ready to go with my trades first strategy, right? Because now I have all the right situations. Each number down below is smaller than the number above, so I can proceed. So 3 from 12 is 9. 4 from 12 is 8. And I get 389. So go ahead and try that on your own. Make sure you get the same answer. All right, now we're going to use the same strategy here with these base 5 numbers. Now, keep in mind this important fact. The first digit here represents the 5 to the 0 power, which is the ones, right? Remember, 5 to the 0 is 1. The second digit is going to represent the 5 to the ones, the number of 5 to the ones we have. And the third is going to represent the number of 5 squares we have, right? So since I cannot take 3 away from 2, I'm going to borrow 1 from this 3 here. So this becomes 2 5s now, and I'm going to lend 1 5 to this 2. Now I have 5 units, right? So 5 units, 1 5 or 5 units. So I have 2 units already. So 5 and 2 makes 7. Now, some people may get real picky here and say you shouldn't write 7, you're doing base 5. But my inside tip for you is you can write it and go ahead and subtract, and this will work out perfectly because you know that you're talking about a 7 in base 5. So moving on, I noticed that I can't take 4 away from 2. So I'm going to have to borrow from this next number, and that becomes 3. So now I have 3 5 squares here, and I'm lending 1 5 squares or 5 5s to this column, right? So I have 2 5s already, so the 5 that comes gets added to that, and now I have 7 5s. All right, remember, rather than this being a number, think of it as a tally of how many of these guys you have now. So how many 5 to the zeros, how many 5 to the ones, and how many 5 squares. Now 3 from 7 gives me 4. 4 from 7 gives me 3. And the 3 just drops down. So I get 3, 3, 4, base 5. And that's how you do subtraction in another base. Very similar to base 10, but you just have to realize in base 10, you were dealing with place values of 10 to the 0, 10 to the 1, and 10 squared here. Whereas here, you're dealing with place values 5 to the 0, 5 to the 1, and 5 squared. That's it. Once you understand that difference, you should be in great shape. You can, of course, quickly check this to see if you've done it correctly by adding 334 in base 5 to 43 in base 5 to make sure you get 432 in base 5. So 3, 3, 4 in base 5. Now we're going to add it to 4, 3 in base 5 and see what we get. So first we notice that we add the ones, so we have 3 and 4. That gives us 7 ones. Of course, we can't write 7 in base 5, so we're going to write 1 5 and 2 ones, right? So we put the 2 here and put the 1 5 up here, right? So now we have 1 and 3 is 4 and 4. We have 8 5s, right? Remember, the second digit is the 5s digit. So we can't put 8, so we're going to put 3 of those 5s here and move 5 of those 5s, which is basically 1 5 squared, up here, right? So now we have 4 5 squares, which gives us 4, which we can write because it's less than 5. Remember, all the digits from 0 to 4 are allowed. So basically we get 432 base 5 as expected. Okay, So you can always check these like you did with base 10 calculations. All right, and the last thing we're going to do for this lesson is look at some mental mathematics tricks with subtraction. One method is breaking up and bridging. So for example, if I want to handle 74 minus 26, first I'll handle something much easier. I'll just handle 74 minus 20, which gives me 54. Then I know that I need to take 6 more away, right? So I just take that 54 and take that 6 away, and I end up with 48. So for this next method, trading off, notice that we know we can get from 26 to a nice number like 30 quickly, so we add 4 there. To keep our subtraction result the same, we need to add 4 on the top. Now we have 78 minus 30, which is a much easier subtraction, and we get 48. And you can verify that by doing this subtraction and realize that indeed you get 48. And the last strategy is called dropping the zeros. Of course, what we can do is, since they both have the same number of zeros, we can ignore them. Just do 74 minus 6, that's 68. But just do remember that you drop 2 zeros, so you need to bring them back in now. So it's basically 6,800 is the result. All right, as is our usual practice, let's go ahead and take a look at a few homework problems. All right, here's an interesting problem that makes you think a bit. We want to know what conditions, if any, must be placed on A, B, and C in each of these problems so that the operations can be performed within the set of whole numbers. So you have to restrict yourself to the set of whole numbers. Remember that if, think about it first of all, as always, see if you can come up with an answer yourself, and then come back to see if we agree. Notice that now that you've come back, hopefully after trying it on your own, notice that for the first part, right, for A minus P to remain a whole number, that means the answer has to be 0 or greater, right? The only way that's going to happen if A is greater than B, right? So, but can it be equal to B? That's a big question. That's fine too, because in that case you would get B minus B, which is 0. So the stipulation here should be A is greater than or equal to B. As long as that happens, the result of the subtraction is going to remain a whole number. Again, if abstract concepts such as letters throw you off, try some real, some actual numbers, right? So actual whole numbers here. So notice if I have like 6 and 4, as long as 6 is greater than or equal to 4, 6 minus 4 is going to be 2, which is a whole number, which is good. All right, and of course, if I had, let's see, I touch something again, and it's always problematic with these touch screen computers because they should be called touchy computers, right? Okay, so if we did 4 minus 6, for instance, notice the outcome would be -2. This does not belong to the set of whole numbers. So that's why you don't want B to be larger than A. So we want to make this stipulation that A is greater than or equal to B. All right, how about this next one? Well, here we have two issues to deal with, right? Firstly, we have this subtraction within the parentheses, this group right here, right? So that right there should also result in a whole number. So that tells me that B should be greater than or equal to C. Once that's taken care of, I'm doing a subtraction between A and this group. So notice that A is going to have to be larger than that whole result as well in order for the result to stay within the set of whole numbers. So not only does B need to be greater than or equal to C, so we need to say and A has to be greater than or equal to that the result of that subtraction right there. So there are two things that we need to worry about when it comes to that particular problem, that second part. Think about that a little bit, make sure it makes sense before you move on. All right, for this next one, we're going to use the counting up algorithm. I've already shown you how that's done in the lecture, but I want to give you a warning about a common error with this method. So let's say we want to deal with part A, and that's the one I'm going to show you. So 82 minus 56, right? So remember, the way the counting up algorithm works is you start with the 56, which is, by the way, called the subtrahend. So whenever you have a subtraction problem like this, the first one is called the minuend. The number being subtracted away is called the subtrahend. And the result is called the difference. So you start with the subtrahend and you try to work your way up to the minuend, right? Now, we know that we can quickly get from 56 to a nice multiple of 10, which is 60, by adding 4, right? Now, I can quickly get from 60 to 82 by adding 22, and I end up with 82. Now, what I wanted to warn you about is sometimes students incorrectly just put the 22 as the result. But remember, you did two trips. First, you did a trip worth 4 units, and then you did a 22 unit trip. So basically, to get the actual correct answer, you would have to combine those to get 26. So you actually need to go 26 units from 56 to get to 82. So be careful with that. That's all I wanted to warn you about. All right, so here we're going to take a look at a base 8 subtraction. We've already done it in base 5. So let's see what it would look like in base 8. So let's look at the first part. I'll leave the second part for you. So 4, 5, 1 in base 8 minus 5, 5 in base 8. Now, remember that the place values here for the first digit are, that's 8 to the 0, or units, right? The next one over is 8 to the 1s, and the next one over 8 squareds, right? So now I know that I can't subtract 5 from 1, right? So I am going to have to borrow. So I'm going to borrow 1 8 from this column. That's going to leave me 4 8s, and I'm going to add that 1 8 to this column. So now instead of having 1 unit here, I add 8 more units, so now I have 9 units, right? Now moving on, I know I can't subtract 5 from 4, or 5 5s from 5 8s from 4 8s, so I'm going to have to borrow. So I come here and I borrow one of these 8 squares. This becomes 3 8 squares. So now I'm going to be adding 8 8s, 1 8 square, which is 8 8s, to this column. So instead of having 4 8s, we now have 4 and 8, so we have 12 8s. Okay, so we've kind of done our trades first strategy. We're ready to subtract. So 5 from 9 leaves me 4. 5 from 12 leaves me 7. And 3 is just comes down. So I get 3 7 4 in base 8. Now notice how it was different from when we did 5, because here when we added 5 5s to this column, but here we're adding 8 8s to this column. So make sure you understand the difference, and you should be in good shape. And be organized, keep things, nice space between numbers, leave room so that you can do things clearly. Remember your place values, all that should, lead to smooth sailing. All right. Try it on the second one here before you move on to your own homework. All right, so here we're looking at an equation. We want to solve 18 minus x equals x plus 6. Now, there's a very common sense rule for equations or equality that tells us if a equals b, then we can go ahead and subtract any constant from both sides. So a minus c should be equal to b minus c. Notice that this constant, of course, has to be the same. Now, if we think of this in that constant context, we notice that one thing we can do is go ahead and subtract 6 from both sides and end up with the new equation, which is equivalent to the previous equation. 12 minus x equals x. So without needing to go into further rules of algebra, which we haven't quite done yet, we can just reason this out, right? What whole number do you know that 12 minus that whole number gives you that same whole number? Now, of course, if you're familiar with doubles, you would know that the number that would fit the bill here would be 6. So here we can say, given that 12 minus 6 equals 6, x must be 6. Now, whenever you propose a solution for a given equation, you always must check your answer in the original equation that was given. So let's see if it works out. So 18 minus 6, we're checking to see if that equals 6 plus 6. Now notice that 18 minus 6 is 12. And 6 plus 6 is also 12, so I can now drop the question mark. I put the question mark because we were checking. Now that I've checked it and it works, I can say check, it works. So there you go. How about this next equation? We have 9 minus x minus 5 equals 1. Now, of course, we can go ahead and notice that using associative properties and commutative properties, we can move these numbers around, and for all practical purposes, we can drop those parentheses. And by regrouping, we can go ahead and take care of the 9 minus 5, which gives us 4. So we have 4 minus x equals 1. So now we ask ourselves, what number do we need to take away from 4 to get 1? And of course, that would be 3. Again, check back in the original equation. We want to know if quantity 9 minus 3 minus 5 is equal to 1 with the question mark because we're checking, right? Now, 9 minus 3 is 6. Minus 5, we want to know if that equals 1. I keep the question mark because I haven't reached the definitive statement yet. Next, I know that 6 minus 5 is 1, and I know I have 1 on the other side. Now I've verified it. So I've reached an identity. So by plugging in the number, I've reached the true statement. Therefore, that must be the correct solution. And that's how you can approach problems like this without getting into too many applications of more advanced algebraic concepts. All right, here's an interesting problem that makes sure we understand inequality. Now, notice that we have the answer here so that you can make sure you're doing it correctly. I want you to try to see if you can reach this with your own reasoning before you continue and listen to me, okay? All right, I'm hoping you did that. Notice that we have A is less than B. And from that, they've gone ahead and give us two inequalities which are in the form of greater than, right? So we're going to write the equivalent of those with less than. So if C is greater than B, what does that tell you? That tells you that B is less than C, right? Remember, the inequality always opens toward the larger number, right? Like that. And this, if you write this in the form of less than, it would become what? C is less than D, right? But they give us one other statement. Once again. All right, we're back. All right, the other statement is the fact that C is less than E is less than D. So we notice that A is less than B, B is less than C, and C is less than D, but C is also, E is also between C and D. So putting all these together using a property we call transitive property, we get A is less than B, which is itself less than C. Now, since we want to get E in the picture as well, instead of using this fact, we're going to use this more refined fact. So we're going to say C is less than E is less than D. So you get one inequality chain that should cover the entire situation. So just think about that a little bit, see if it makes sense to you before you proceed. All right, here's a nice example with properties. Ashton claims that if he eats 8 cookies and eats 3 of them and later eats 2 more, actually not eats 8 cookies, has 8 cookies, sorry, has 8 cookies and then eats 3 first and then 2 later, this is the same as having 8 cookies and then eating 2 and then 3. He says this is the commutative property of subtraction. How do you respond? Well, you got to be very, very careful, because if you remember, we do not have a commutative property for subtraction. If you recall, A minus B does not generally equal to B minus A. This doesn't, remember, when we say A minus B does not equal to B minus A, we don't mean it's never so. We mean there are cases where that doesn't happen, such as 2 minus 5 is not the same as 5 minus 2. So to better depict what's going on with Ashton, he starts with 8, then takes away the 3 and the 2 in this manner, in the first scenario, right? So it's 3 and then 2, so then you're going to take that away, that group away from 8. In the second scenario, starts with the 8 cookies and then first eats 2 and then eats 3. And of course, this is true, but it is not the commutative property of subtraction that is being used. It's the commutative property of addition that is being utilized. That's how you would correct Ashton. All right, I think that's a good place to stop. We should be okay on the homework now, so take care and we'll see you for the next lesson.